Right, okay, everyone. Just thought to do a quick video to give you some not feedback, just to show you about a little bit on the principles. The work I have set for you is in, let me just share this with you, is in Microsoft Teams. There's all the different lessons I've set for you. This is the Friday group session here. So you guys have got extra material on inspection and testing as well as fault finding there. The one I want to particularly go over with you is this reactance and impedance. This is a particularly complex assignment, this one. If we have a look, let's have a look at somebody who's not bothered doing the work. Kyle, right? This is his worksheet here. There's a lot of questions in this, and I didn't expect you to get them all done in one go. So what I'm going to do right now is I'm going to go through a few of the questions and make sure that you understand what you were supposed to do. First of all, stating the effect that an inductor has on an AC circuit. It's as simple as the inductor. Remember the word civil that we were talking about? The capacitance causes current to lead voltage, CIV, and inductance, L, causes current to lag behind voltage, right? It lags by 90 degrees. So a simple answer to that question, the effect an inductor has on an AC circuit, the inductor causes the current to lag behind the voltage by 90 degrees. And you can also say almost the same thing there if you look at question 2. What's the effect does a capacitor have? Capacitor causes the current to lead the voltage, and we know it's by 90 degrees. So then question 3. Question 3. You really need to know about reactance before we do that. We'll come back to that. The phasor diagrams we did in class, right? So if you remember, the phasor diagrams were just like a chart. Let me show you that one. Phasor diagram showing the relationship between voltage and current for resistor, inductor, and capacitor. So if I show you what kind of drawings we're looking for that, right? We were after, for resistance, if you imagine that didn't know what was supposed to happen, go big. Right, so if I do draw and freehand, hopefully that'll do something, right? So if you imagine a graph like that, your voltage, if it is, you start with your voltage is always your reference point, goes along that way. There's your voltage. And your current, if it's resistive, the current is in line with the voltage, so the current goes along there as well. So there's your resistive current phasor diagram. If it's inductive, right, still my voltage is on that line, right? Now, if you remember, my inductor causes me current to lag behind my voltage, civil. If you remember that, let me just write that at the bottom of the page. Right? So if the current lags behind the voltage, you remember on these graphs, they go anti-clockwise, don't they? There's 0, 90, 180, 270, back to 360. They go anti-clockwise. So if the current is lagging behind the voltage by 90 degrees, then the current is there for inductive. All right? And then with capacitive, there's my voltage again, right? And remember, civil, capacitance causes the current to lead the voltage by 90 degrees, so my current must be there. All right, so that's the kind of graphs we're looking at for that. If we go back to the document, wherever it is, there. Right, so this is your assignment. So they were the diagrams we were looking at for that. Where are we? So there they are. Right, now we're into all right, so this question here, question 1, as the frequency increases, says in a circuit that consists of pure inductor, explain what happens if frequency increases. So if you remember the equation for this one, for an inductor, the equation was 2 pi FL, right? Now, if you forget about 2 pi F and L, sorry, 2 pi and L, right? Call them 1, right? 1 times 1 times 1 is just 1, right? as the frequency increases, it's a multiplier. So then the reactance, remember XL, reactance, is equal to 2 pi FL. If the frequency increases, then the reactance must also increase, right? So then let's look at the equation here in question 2. The inductance is 0.1 henries, voltage is 200 volts, frequency is 60 hertz. Calculate the current drawn from the supply. Now, if you look at this question, the next, so we got inductance, looking for calculating current. Next one, we got an inductor again, calculate current. It's exactly the same question with different numbers. The fourth one, inductor, as a reactance this time, 4 kiloohms, right? But it's voltage again. It says calculate current. You don't need frequency, do you? If you want current and you got voltage and resistance, remember Ohm's law, V over R equals I. That's all it is. Voltage over resistance gives you the current. So that one again is actually even easier than question 2 and 3. Question 5. Again, let's have a look. Pure inductor, calculate the current. It's actually asking for exactly the same question as 2 and 3. So we've got frequency. We got 2 different frequencies, so it's asking us to do it twice. We've got henries and we've got volts. So if we have a look at question 2, we've got 0.1 henries, 60 hertz, 200 volts, and we're looking for current. So let's have a look at what that should be. Right. So if we clear the screen, can I clear the screen? Yeah, I can do that. Clear all drawings. Right. So now we've got the equation XL is equal to 2 pi FC, FL, U undo L, right? Where L is equal to 0.1 henries. Frequency was equal to, I can't remember, I think it was 50 hertz, was it? Let's have a look. What was it? The frequency was 60 hertz, and it's 200 volts. So don't forget that, Steve. 60 hertz. Right, so F was equal to 60 hertz, and my voltage is equal to 200 volts. Now, obviously, in this equation, there's no room for voltage, is there? So we must be using that to find the current at the end, which is going to be Ohm's law. So we need to find the reactance to be able to divide the voltage by the reactance to get current, don't we? I, remember, I is equal to V over R or XL, right? Because XL, although resistance and reactance aren't exactly the same, they still work the same for Ohm's law. So if we put these numbers into our calculator, right, 2 pi in your calculator, F is 60, L is, so we got 2 pi times 60 times 0.1. If we put that in our calculator, let's have a look. Screen share again. Where are we? New share. All right, let's have a look at this one. This is the application now on your phone that I said you can download. All right, so you can get this one for free on an Android phone anyway. 2 times shift pi times 60 times 0.1 gives you 3.77 ohms. Okay, so use 3.77. Back to our thing here. So then this equals, so XL equals 3.77 ohms, right? So then 200 volts over 3.77 gives us our current. So I is equal to 200 over 3.77. So then we can go back to our calculator again. All right, let's clear that. So 200 over 3.77 equal to, we got 53 amps. Okay, so that equals 53 amps. Okay, so that is all you have to do for about 4 questions there. If we go back to our work, so we got question, so you can answer question 2, 2, 3, 4 is even easier because you don't have to work out the inductive reactance it's given to you. So it's just 24/4 there, 4K, don't forget. Then you've got the next one, you got 15 millihenries, which you can do 2 pi FL to find your reactance. And then you're just going to do it with the 2 different frequencies. You're going to do 2 pi FL with 15, 2 pi FL with 2.5 kiloohms. All right. So you're going to have 2 different answers for that, but it's exactly the same question. Number 6, calculate the inductance. So that's just 2 pi FL, so it's not even working out current. Number 7, coil, calculate the current again. So that's exactly the same question with different numbers. So you should be able to do all those with that one example I've just done for you. The capacitance, what's this? Explain the relationship between current, between voltage and current in a pure resistive, inductive, pure capacitive circuit. So remember the graphs we did before? Exactly the same question. Reactance opposes current flow. Explain what capacitive and inductive reactances oppose. Hang on, what's that question? Resistance opposes current flow. Explain what capacitive and inductive reactance oppose. They oppose a change. Your inductive capacitance opposes a change in current, and your inductance opposes a change in voltage. Or is it the other way around? Yeah. Your capacitor opposes a change in voltage. Your inductor opposes a change in current. There's a couple of little equations for that one, which I'll leave you to find, but it's it's C is equal to dV by dt, and L is equal to di by dt, which if you ever look online, you'll find them. Then what's this? So here we go. Very similar question to what we've just done. A pure capacitor has a frequency, it's connected to 60 hertz and then to 30 kilohertz. So this is like the harder one. Here's a simpler one. Notice it's calculate the current again. So 650 nanofarad capacitor, 12 volt supply, 100 kilohertz. So let's have a look at how we would work that out. Whiteboard. Let's clear this. Clear all drawings. Right. So your capacitor. So don't forget your equation for your capacitive reactance, XC, is equal to 1 over 2 pi FC. All right. And we got a capacitance, which was 640 nanofarads, or 640 times 10 to the minus 9 for nano. All right. And we had the frequency was equal to 100 kilohertz, wasn't it? Which is 100 times 10 to the 3. Okay. And the voltage, I can't remember what the voltage was now, it was 12 volts. All right. So if we plug these two numbers into this equation, we can find our capacitance. So we'll get XC is equal to 1 over 2 pi times times 100 times 10 to the 3 times 640 times 10 to the 9 minus 9. Okay, so let's have a look at how that works out in our calculator. Okay, so we've got, oh, didn't mean to do that. Go back that way, right. So we got 1 over 2 shift pi times 100 times 10 to the 3 times 640 times 10 to the minus 9 or negative 9. And we've got 2.49. Okay, 2.49 ohms for that one. Rounding it up. We'll go back to that. Oh, no, not that one. The whiteboards are on, aren't we? So that then equals, so XC equal to 2.49 ohms. And the same as before, your current, sorry, I, is equal to V over, now it's XC, which gives you 12 over 2.49. And we get, for the current, back to my calculator. All right, we've got 12 over, and I'll put my answer in there, can't I? All right, 4.83 amps. Okay, 4.83 amps. So that equals 4.83 amps. All right, so we'll go back to our homework. And there you go. So this question here is 4.83 amps, right? Showing your work, and I expect to see you working. If you're not doing any working out on here, I can't tell. If you get the wrong answer, I can't see where you've gone wrong if you don't do any working out. So this one here was exactly the same question. You just had two different frequencies. That means you have to do two different currents, don't you? Because if you change the frequency, you change the current. Is there one about what happens as the frequency increases, like there was with the inductance? Oh, there you go, yeah. A circuit with pure capacitance, what happens when the frequency increases? Now, this time, because it's inverted, you got 1 over 2 pi fc. That means it doesn't matter what you divide by 1 by. If you increase the denominator, the total value is going to go down. You divide 1 by a bigger number. So as you increase the frequency, the capacitive reactance is going to go down. So it's like the mirror image, isn't it, of the inductor? All right, so that's all your capacitor questions. You should be able to do all them with what I've just told you. The last one, this is where we really need to get to. This is where it becomes more difficult. This is your impedance questions. Now, this is where impedance is where you include resistance and reactance, and the reactance can include inductance and capacitance, right? So you can get something called an RLC circuit, or resistive inductive capacitive circuit, right? So have a look at this first one. It's got inductance and resistance. So this is just an RL circuit, right? Where you've got these two together. Our first task is to find out what the inductive reactance is. So we've got the same question again. We've got 2 pi FL, first of all, to find out what inductive reactance is. Okay, so if we do that first, let's just clear our whiteboard and we'll go again. What was the inductance again? 0.04 henries. Okay. So we share that. Let's clear this. All right. So we got XL. Oh, didn't mean to do that. So we got XL is equal to 2 pi FL, where L is equal to 0.004 henries. Doesn't look like, now it looks a bit like a 4. Anyway, so we can put our equation in. What was the frequency? Oh, I forgot what the frequency was. Right, let's go find out what the frequency was. It was 50 hertz. So back to our whiteboard. So we've got frequency. So F is equal to 50 hertz. So our first step, XL is equal to 2 pi times 50 times 0.04. Let's find out what that is. All right, so we got 2 shift pi times 50 times 0.04, and we got 1.26 ohms for that one. 1.26 ohms. So that equals, where are we? 1.26 ohms. Right, and the question was to work out the current. So to work out the current, we need to do the same as before. V over R is equal to I. Now in this case, we haven't just got resistance, we've got resistance and inductance. So we got, instead of V over R, it's now V over R plus XL. But you can't just add these two together. They don't add, right? So it's, what we often do is we put a J in front of that just to say to you, it's not resistance, it's reactance. You cannot add these two numbers, right? Effectively, that's actually called a rectangular number, or Cartesian, but you're not interested in that right now. All we need to remember is you cannot add those two together, right? If you do, you're going to get the answer wrong. So let's have a look at what the resistance was again. The resistance was 8 ohms, and we got 100 volts. Okay, so let's go back to this. So we got 8 ohms, so we got R is equal to 8 ohms, and voltage equal to, was it 100? I can't even remember if it was 100 volts or not now. Let's go with that. Go with that. So if we can't add these two together, how can we find a total impedance value, right? Our total impedance we call Z, and we calculate it exactly the same as you would with a triangle. If you remember, our resistive value is on the 0 degrees line. Our inductance, this we've written it 1.26, that's on our 90 degrees shifted line. That's over here, right? 90 degrees shifted from normal, so that's 1.26, and this is 8 ohms here, right? You can't add them together because they're both going different directions. They're pulling in different directions. If you imagine this is like a tug of war, this guy's pulling this way with a force of 8 newtons. This guy's pulling this way with 1.26 newtons. This center point here, whoever's standing there, isn't going to stay in the same place. They're going to go in some, probably more this sort of direction, right? But it won't stay still because there's no force acting this way to stop them moving. So there's some equivalent force, right? Or some equivalent resistance, which you call impedance. And the actual strength of it is this length here, which, as you can see, would be the hypotenuse of this triangle. So all we need to do then is use Pythagoras' theorem to work out what this length would be. So this would be 8 squared plus 1.26 squared, right? So we get total impedance with those two values. So if we have a look at that on our calculator, I didn't get the numbers actually. What were the numbers? We've got 8 and 1.26, haven't we? 8 and 1.26, right? So let's calculate that. So we've got 8 squared plus 1.26 squared, and we get 8.1. Let's go with 8.1. All right, so this is equal to 8.1 ohms, right? So now we can do I is equal to V over Z, which equals 100 over 8.1. Now this number, what you need to remember is this number is always going to be, when you're talking about the hypotenuse, it's always going to be longer than the other two lines, longer than both of them. So you know that number's about right at 8.1. So let's calculate that anyway. So we get 100 over 8.1. Back to our calculator. We got 100 over 8.1. I've got 12.35. 12.35 amps. There you go. 12. Oh, it's upside down. 12.83 was it, amps? There you go. So that then is our current. So notice we had to get our inductance first. We had to find our impedance by doing Pythagoras, and then we can finally do Ohm's law. to work out the current. So if we have a look back at our assignment, okay, there you go. The current that will flow in that circuit was 12.34, was it? Yeah, 12.35 amps. Okay, so you can do exactly the same. Notice this is exactly the same question there. Number 2 is exactly the same with different numbers. Okay, so practice yourself with that question. Number 3, this one now has got a capacitor. So it's exactly the same question again, but your inductance, sorry, it's not inductance, it's capacitance. So instead of doing 2 pi FL, you do 1 over 2 pi FC to get your inductance, sorry, your reactance for that capacitor there. Okay, exactly the same question for number 3. Number 4 is the same question again, same numbers, just wants to know the impedance, which is the Z that we worked out in the previous question, and the current. Exactly the same question. It's just asking you to recognize what the impedance is, which is when you do Pythagoras. Question 5. We've now got, hopefully, an RLC circuit. This is where it becomes, it's more of the same, it's just more detailed, right? If you notice, you've got to work out your inductive reactance, your capacitive reactance, and you've got a resistance there. So it wants to know your inductive reactance, your capacitive reactance, and your total impedance, and then your current. Okay, so let's do this question, and I think once you can do that one, you've cracked it. Right, this is as hard as it gets, this for impedance. So let's just take those numbers. So what have we got? I think I can do it with it another way. Let's just clear this, clear all drawings. All right, so what have we actually got? So we need, for this question, we need to remember our XL, XC, we know our voltage, we need our frequency. I think that's all we need from this question to be able to calculate everything. It's not XL, yeah. So XL is going to be 2 pi FL. XC is 1 over 2 pi FC. So then we need L and C, don't we, to be able to calculate those two equations. So let me just see what the actual numbers were. It is not that one, it's this one I need. So we've got 0.318, 38.9, what's that? 0.318, 38.9, 0.318, show you. Yeah. 0.318. I can't remember. That's Henry's. I should put Henry's down there. I got such a bad memory. What was that then? 38.9 microfarads. We got 38.9 microfarads. And we got 20 ohms. We need resistance, 20 ohms, 50 hertz, 230 volts. Okay, I think we can do that. 20 ohms, 230, 50. So we got resistance, 20 ohms, that was 230 volts, and that was 50 hertz. Right, so we can go from here once we've got all this down. First of all, we're going to calculate this one. Right, so that's 2 times pi times 50 hertz times 0.318. We'll calculate that. This one is going to be 1 over 2 pi times 50 again times, now it's 38.9, and it's micro, so it's times 10 to the minus 6. What's that going to be? All right, so we'll calculate those two. Let's get our calculator. So we've got 2 times pi times 50 times 0.318. We've got 99.9 ohms for that. So we put that in. So that's 99.9 ohms. And in fact, if we remember, it's not a real resistance, so we should put a J in front of that just so we don't forget. Right, and the next one. Right, so we got 1/2 times pi times 50 times 38.9 times 10 to the minus 6 because it was micro. 81.83. Okay, 81.83. All right, 81.83. And again, it's ohms, and because it's not real ohms, it's reactance. It's J in front of it. Okay, so now we've got resistance, inductive reactance, and capacitive reactance. So now we need to remember that our resistance, 20 ohms, goes along our zero line for our graph. Our inductance is lagging behind the voltage there by 90 degrees. That's 99 that way. And our inductance is going ahead by 90 degrees, so that's 81.3. So these two, you can see, are directly opposing each other. So in calculations, we can say that this is equal to XL minus XC, right? If we do that, we get a total on this line, right? 99.9 minus 81.3. Right. Let's calculate that. We got 99.9 minus 81.3, was it? I can't remember. Answer. Oh, no, that's not right. 99.9. I forgot to put the point in, didn't I? Minus 81.3, I think it was. Okay, 18.6. All right, so that is 18.683 it was. We'll just go with this anyway. 18.6 ohms. Now don't forget that's J, it's not real. So effectively this then now becomes a right angled triangle, 18.6 that way and 20 this way. So our magnitude of impedance is there again, isn't it? So Z is equal to the square root of 20 squared plus 18.6 squared. So then Z is equal to, let's have a look at that. It's going to be bigger than 20, isn't it, if you remember? So square root 20 squared plus 18.6 squared, 27.3. So we've got an impedance Z of 27.3 ohms. Don't forget, sorry, this is now impedance. We can use this in our Ohm's law, V over X, right? Or V over Z, I should put, shouldn't I? And let's get rid of that. Let's just change that. V over Z, which equals voltage, which was 230 over 27.3, gives us a current of 230 over 27.3. 230 over 27.3, 8.42 amps. So that is 8. Where am I? 8.42 amps. So if you look at the question again, it asked us for XL, which we worked out at the beginning, there. Asked us for XC, which we worked out there. Asked us for Z, which we calculated here. Asked us for the current, which we worked out there. Okay, so that's our 4 answers. All right. So if we go back to our assignment, where was it? There. You should now be able to answer. Notice there we had XL, XC, Z, and current I. So you should be able to complete, even following my numbers, you can do that question. I'd like you to try it out at least answer the questions describing what you've done. Okay, and let me see how you get on with these others as well, because I can see by the others if you understood the last one as well. Okay, so I'll leave that one with you, and just oh no, I need to share again. I want to show you one more thing before we carry on. In our Microsoft Teams, all right, if we close this, where are we? All right, go back to our assignments. Right, as you can see, I'm not getting great responses on these. This is for continuity. These ones are really straightforward for most of you who haven't done it. All right, let's have a look at this. This was last week's work, most of you haven't done yet. All you got to do is read through this bit of text, have a scan through it. At the end, you've got a few questions. All these answers are in the text, right? I don't want you to copy and paste. I want you to write your own answers. Well, look, state the reasons for conducting a ring file continuity test. You probably know most of these answers anyway, so let's just see you write your answers, all right? No copying and pasting, all right? So that is all I'm going to do for today. So if you need me to clarify anything I've been through, you feel free to email me. I can do more videos. I can slow it down. I can do different examples. If you've got one particular question you need me to help with, send me that question and I'll help you with it. But basically, they all follow that same process I've done with each of those questions. Okay? Make sure you read the questions properly. And I'll see you soon, hopefully.